First tutorial is making an XY scatter plot in Excel. The data that we have here is absorbance of 6 different solutions as a function of the concentration of this potassium dichromate in solution. We also have the molecular weight in grams per mole of this compound. And so notice that the concentration is in milligrams per liter. We're being asked to make a plot of absorbance versus concentration in units moles per liter or molarity. So we need to convert this using the formula weight in Excel. So let's do that quickly. So start by making a new column here. We'll just label this concentration. In parentheses, we'll put big M for molarity or moles per liter. Then we'll type in a formula. We'll click on the first cell, type equals, and then we can either type our formula up here in the formula bar, or we can type it directly into the cell. And what we need to do to convert from concentration in milligrams per liter into moles per liter is we need to get milligrams to grams, and then we need to get grams to moles. So there's 2 steps here. So first step would be to, you can put a parentheses here, that can't hurt, would be to take our concentration, click on that cell, and then we'll do divide by 1,000, and that will convert from milligrams to grams. And I'll close that parentheses just to close that operation. And then I need to divide that whole thing again by the formula weight to convert those. And I would do the dimensional analysis here on paper just to convince yourself. And in doing this, I could select enter and be done with this, but eventually I'm going to want to drag this formula down and populate each one of these concentration values so this automatically computes. If I do that right now, what that's going to do is it's going to change this value in my column C, but it's also going to drag this down. So it's not going to keep this fixed on this constant, which is what I want. And if you want to fix a cell in a formula so it doesn't move as you drag others, then you can highlight that, and then you can either type or hold F4 if you have that on your keyboard, or just manually add a $sign before the column label, which is B, and a $sign before the row label, which is 1. That will fix it in the formula. So let me click enter. Of course, I'm multiplying by or dividing into a 0 here, so it's not going to do anything. But if I now click and hold and drag this down to the bottom, you can see that's going to populate my formula. And let's just click one of these to see what the formula does. You can see that it's grabbing this first cell, which is what we want. It's converting this concentration, but it's still calling upon this constant. And see how it didn't drag this down by 5 cells in the same way it dragged this down by 5 cells? That's because of that $sign. So that's a nice trick. Okay, second step here is to make the actual scatter plot. So we'll go to Insert on the tab here. We'll go to Charts, and then we'll choose Scatter. And we'll end up with just a blank chart here. And I need to select which data I want to use. So I'll right-click on this, and then choose Select Data. Now I can choose which series or entries I want to include. So I'll choose Add, and now it's going to ask for a name. I'm just going to leave that blank, and I'll choose my X values. So here I'm making absorbance on the Y as my dependent variable, concentration as my independent variable on the X. So X is going to be concentration, and it's going to be the units that or the values that we just computed in molarity, and then the corresponding dependent absorbance values then would be on the Y over the same range. I'll select those, and that's all I need to do. And you can see it's pre-populating that data. It's a nice straight line. I'll click OK and OK. So that is the basic form of making the scatter, but this would be an ineligible scatter plot in any class or any scientific journal. We need to format it in the appropriate disciplinary way. And in all STEM, graphs never receive a title. So we're going to delete that title just by clicking delete. And all graphs always, under all circumstances, must have axis labels with appropriate units. Without them, it's a meaningless graph. We don't really know what these numbers pertain to and what this relationship is. So the first thing we'll do is add axis titles. So we'll click this plus button, click axis titles. That's going to give me some generic label, axis title for both, that I'll manually populate. So my x-axis here is going to be concentration, and I can just double click this if I want to save some time and copy that, and I can go over to my axis title here and paste that in. And you can do the same for the y-axis. And remember, the conditions I need here are that I need axis labels explicit on both axes plus units. And so absorbance has absorbance units, AU denoted here, concentration has units molarity. I have no chart title, so this is a completely acceptable and appropriate graph. Okay, so to find the functional relationship between an independent and a dependent variable, we can fit it to some sort of mathematical model, a function. And the simplest function is the equation of the straight line, which is y equals mx plus b. And we can see already that that's a pretty good fit for a linear model. And we often use that model because it's one of the easiest for us as humans to understand. And so first thing we'll do is add that trend line. And so I can choose the plus chart elements, go down to trend line. I can click that trend line. You can see it automatically add. And then I'm going to go down here to more options because the trend line alone is not the only useful thing. And if it doesn't populate already, it might give you some options for changing the appearance of this line. That's not what we want. That's this paint bucket option. We'll go over here to these bars on the right, and this is what we want. This is where you can actually change the mathematical formula to a log or a polynomial or a moving average. We almost always use linear models because they're the simplest to extract meaningful information from. And what I want to include here is to display that functional relationship, the true equation, on the chart, and I want to display the r-squared value, which is called the correlation coefficient. So you can see both of those. They're small here, but they've been added to the chart. We can change the size if we'd like. So you can see the equation is y equals and then some number x plus some number. So that is the y equals mx plus b, but this first number, that is the slope of this line. That's the rise over run, times some value x, and then that's added to this value at the end, which is b. That's our y-intercept here, just above 0. And below that, the correlation coefficient is r-squared. And the correlation coefficient is a statistical entity that establishes how close the numerical data in the actual data set fit this projected line or the projected equation of the line here. So a perfect fit of data points on this line would give us an r-squared value of 1.0 or 100% fit. Here we're talking about 0.9988. So this is a value that indicates how close the model fits the data. So this can be really handy if we want to take the equation of the line and write it down somewhere else, maybe a lab notebook, or put it into another program. But often we want to use that data exactly, or this equation exactly, to then predict from some measurement of absorbance what the concentration of some unknown thing would be. In other words, we measure something here and we trace it over to the line and down, and we can determine the unknown concentration. That's the real utility of this type of numerical or functional relationship. And so to do that, we would still have to punk these numbers into our calculator, or we can do a more direct computation of that. And so I just typed out slope and intercept and r-squared here. But we can just extract that directly with a formula in Excel, which is super convenient if we're going to use those values. So I can just type equals and then slope, and you'll see it pop up, returns the slope of the linear regression line through the given data points. So I'll put a parentheses, and then it tells me I want to put the known y's first, then a comma, and then the known x's. So the known y's here would be my absorbance values. So I'm just going to grab those, and then delimit with a comma, and then I'll put my known x's, which are concentration and molarity, and then I'll close my parentheses and press enter. And you can see that returns this value of slope, 3155, which is exactly the same 3155 up here. But now this is an accessible number that I could use in a subsequent calculation in Excel rather than having to punch this into my calculator. Same thing can be true with the intercept. That's going to be equals intercept. And then same thing, it's going to ask for the known y's, comma, known x's, close the parenthesis, enter. And then for correlation coefficient, The formula is equals CORREL or CORREL, and then we can plug in the total R data, which is going to again be the known Y absorbance, comma, known X's, and then close that and click enter, and we end up with our correlation coefficient. Okay, so why this is really handy to have it in this format directly is now, if in our measurement, which we often do, we now have a data point where we measure the absorbance of a solution. It's a colored solution, but we don't know its concentration, and it comes out as 0.819. We know that falls somewhere in between our lowest and our highest, so that's 0.819. It must land somewhere here, which means its concentration is somewhere here. But instead of just guessing from the graph, we can just solve directly. So this is a Y value. We can plug in for Y here, and then we can solve for X. And so this is the utility of the functional relationship we have here. And so we can set that up. So we'll just go, I just typed in concentration of unknown. So we'll set this as an equation. So we'll say equals to set up a formula. And I'm going to start it with a parenthesis here, because if I'm plugging this in for Y, then I will start with this value, and then I'm going to subtract from that my intercept value to get this value over here, and then close that parenthesis and divide by my slope here. That will solve for X. So then I can just divide there, solve. And so here in units of molarity, we have just solved for the concentration of an unknown solution that we measured the absorbance of, but we converted that to the concentration from this, what we call calibration curve, or this relationship between absorbance and concentration for our given spectrophotometer.